Hello students. So today in disconnection approach, I will discuss the disconnection of alkenes or retrosynthetic analysis of alkene. So if you remember the reactions of alkene, then alkene can be synthesized by various ways. One of the way is by reduction of alkynes or dehydration of alcohol, or it may be synthesized by the dehydrohalogenation of alkyl halide, or if we have any carbonyl compound, it reacts with Wittig reagent to give the alkene, that is the Wittig reaction, or by the Retrosynthetic reaction also the alkenes can be synthesized. So means one of the way, that is the reduction of alkyne or via dehydration of alcohol, or you can do via dehydrohalogenation of alkyl halide. Or if we have any carbonyl compound, it reacts with a Wittig reagent to give a alkene, that is the via Wittig reaction also. You can write Wittig reaction, Diels-Alder reaction, okay. So now let's see one by one. One is the reduction of alkyne. First one, via reduction of alkyne. So if you have any target molecule, let's take one of the target molecule. So suppose this is the target molecule alkene. Now for this target molecule we have to generate the synthetic equivalent or reactants. So how can we do this? Via FGI, means this can be converted into alkene, can be converted into alkynes. So you can do the FGI. If you would do the FGI, then convert it into alkyne. Now after this alkyne, you can do the disconnection. So we can disconnect it from here, carbon-carbon disconnection. So what you will generate? You will have the synthon corresponding to this synthon. You will write the synthetic equivalent, and okay. Now this can undergo, so now using these two, so these are the synthetic equivalents. Now you can write the synthesis. So if this is the retrosynthetic analysis of this target molecule, you can write the synthesis in reverse direction. So you have these synthetic equivalents. Now first of all, from here you will go here, means this terminal alkyne that can be converted into acetaldehyde. So how we can convert it? Means we have to remove this acidic hydrogen, and acidic hydrogen can be removed in presence of, suppose, sodamide. So you will have a acetaldehyde. You will have this acetaldehyde anion, and now this in presence of this alkyl bromide, this bromine will leave out, and you will have this alkyne. Now this can be converted into, this alkyne can be converted to target molecule via reduction in presence of palladium H2 BS4, that is we will use the Lindlar's catalyst here. So this Lindlar catalyst, and this will give you the cis alkene. You will get the cis alkene like this. So if we are using sodium in liquid ammonia, then you will get the trans alkene. You may get the trans alkene. Okay. So this is the via reduction into alkene. So here you can write the reduction. Now let's see example of dehydration of alcohol. Okay, so let's see one of the example. If you have a target molecule, this is the target molecule. So how can you disconnect it? Via FGI. First of all, we can do the FGI, and this functional double bond that can be converted into the alcohol. So OH. So I have added OH over here. Okay, and this will undergo the dehydration. So this will undergo dehydration in presence of H2SO4. We can do the dehydration. It may be protonated to give the H2O. H2 will leave out, and the positive charge will be created on this carbon, and the H, and again the catalyst H plus will regenerated here. Okay, so this will do the after this FGI you have this alcohol. Okay, so suppose if you are adding this OH over here, then you are adding the OH on the secondary carbon. So the preferred way is to add the OH over this tertiary carbon. Okay, now it can be disconnected. I have given you the strategy for the disconnection of alcohols. So it will be disconnected from here. One carbon disconnection will occur, and you will get this is one of the synthetic equivalent, and next one is this. So corresponding to this synthetic equivalent, you can write the synthon. Corresponding to this synthon, we can write the synthetic equivalent. This is one of the cyclopentanone, and so these are the reactant or synthetic equivalent. Now if we can write the synthesis of this target molecule in a reverse direction. So if you write the synthesis, then what you will write? This undergo hydrolysis to give you this alcohol. Okay, so now this can further be dehydrated in presence of H2SO4. In presence of H2SO4, it will undergo dehydration. You will get the target molecule. Okay, so this is one of the example, and another example, suppose if you have a target molecule, if this is the target molecule, the target molecule. Okay, this is another alkene. Now this can also be converted into alcohol by FGI. So what you will do, FGI, where you will add this OH, you will add this OH over this tertiary carbon. Okay, and H is present over here. So we will add the OH at the second tertiary carbon, not here. So after this FGI, you can write the this is clear. Now you can do the disconnection. So if you are doing the disconnection, so as I have told the strategy for the disconnection of alcohol, you will do the disconnection from suppose here. So this will have the positive charge, this will have the negative charge, and what would be the synthetic equivalent? Synthetic equivalent negative, you may add the MgBr over here. Okay, you may add the MgBr over here, and plus you will have positive charge over here. Okay, so the epoxide. Okay, here, so it will form the epoxide as a synthetic equivalent. Now you can write the synthesis in reverse direction. If you write the synthesis, then you can write it. Here, so you will get the alcohol. You will get the alcohol after workup. You will get the alcohol, and further dehydration, you will get the target molecule. After further dehydration, you will get the target molecule. Okay. So after this, you can write as above. Clear? So now next pathway via dehydrohalogenation of alkyl halide. Dehydrohalogenation of alkyl halide. Okay, now suppose if we have a target molecule, this is your alkene, then via FGI this functional group double bond is converted into alkyl halide, because we can synthesize this alkene by the dehydrohalogenation of alkyl halide. So by FGI it would be this target molecule that would be converted into alkyl halide. So we can convert it into alkyl halide. Suppose if we have Br over here. Okay. So no doubt the Br bromine is added over here, not here, because if this hydrogen after dehydrohalogenation, this suppose this H is present over here, then this base will abstract out this hydrogen and this will go over, and this bromine being the leaving group, it will leave out. So that's why you have added this bromine over here. And now after this, again the FGI can be done, and that can be converted into, so this OH, if you think in a reverse direction, in presence of bromine, phosphorus pentabromide, that can be converted into halide, and now it can be further disconnected. Okay, so disconnection, 1,2 disconnection, 1,2 carbon-carbon disconnection. So you will have the R minus plus OH here positive charge. So synthetic equivalent would be this plus one of this epoxide ring. So if you write the synthesis of this, then you can write the synthesis easily. You have this Grignard reagent. Epoxide is prepared because this can easily be broken out. This epoxide ring can easily be broken out, being the very strained one, it can easily be broken down. And this will give you okay, this is a numerite. Okay, now this in presence of phosphorus pentabromide, that is converted into your and dehydrohalogenation in presence of target molecule. So this is via dehydrohalogenation of alkyl halide. Now next way, let's see the example of this Wittig reaction. Via Wittig reaction you can see it. Okay. Suppose if we have via Wittig reaction, if you have example of this, if you have this alkene, if you have to generate a target molecule for this alkene, then we can convert it into the via FGI, we can convert into one of the carbonyl compound which is readily available, this one, and then triphenylphosphine. This is the ylide. This is called as the ylide. And this ylide, this can be obtained from, if we do the FGI again, this can be obtained from methyl bromide and plus triphenylphosphine. Okay, so methyl bromide plus triphenylphosphine, it will give you the ylide. Ylide, after reacting with cyclohexanone, it can give you this target molecule. Okay, so if you see, then I can write the synthesis. Here, and then in presence of base you will get this ylide. Now so this will give you the 4-membered cyclic transition state. You will get a 4-membered cyclic transition state. It's a 4-membered cyclic transition state, and now this carbon oxygen bond, weakest bond, it will undergo fission and you will get the triphenylphosphine oxide. So this target molecule can be obtained. So this is one of the biotic reaction. Otherwise, we can also, this is a cyclohexanone carbonyl compound is generated here. So otherwise, if you can do FGI, but this is not the good path. So after this FGI, we can also get the formaldehyde from here. We can also get the formaldehyde. So you may also get the formaldehyde. This one plus and another you will get the this ylide. Ylide may be this may be the ylide. This may be the ylide. But this using this formaldehyde and this ylide, this is not so much good workable reagent. So better we can convert into the cyclohexanone, which is easily available, solid in nature. So that's why we will follow this path. Okay. And next, this via Diels-Alder reaction, simply via Retro-Diels-Alder reaction. Okay, via Retro-Diels-Alder reaction. So this is the way, this is the different methods for the disconnection of alkenes. So in next lecture, I will discuss the disconnection of alkynes. Thank you.